Okay, this is UBC Math 100, Past Final Exam 2015, question number 9. It says a business wants to manufacture a huge closed box with a square base and a square top and rectangular sides. The material used for the 4 upright sides of the box costs $2 per square meter, and the material used for the base and top of the box costs $8 per square meter. Find the dimensions of the box with lowest possible cost that has volume of 32 meters cubed. Okay, so first off, what are we trying to find? Trying to find dimensions of the box with lowest possible cost with a certain requirement, a volume of 32 meters. What kind of style question is this? Well, it's an optimization question, right? We're trying to optimize for the lowest possible cost. Okay, so how are we going to do that? We want to find cost as a function of some variables. Okay, now for the box, we might want to first sketch out the situation. So we have a box here. It has a square base. So I'll try to draw these two lengths the same. And the height, we don't know what it's going to be. So I'll just different. There's our box. And because it's a square base, that means that whatever this length is, it's also this length. So I'll say x and x for both of the lengths. Whereas the height of the box, it doesn't have to be the same as the base length, so I'll call it h. Okay, the question is, based on these dimensions, what is the cost of the box? Now, to figure out the cost, there's two parts, because there's two different costs, right? For the upright side, it's $2 per square meter, and for the base and top, it's $8 per square meter. So what I'm going to basically do here is add up the cost of the top and base, those could go together, and the cost of the sides. Now, here's the thing. How do we figure out the cost of the top and the base or sides? Well, in general, the total cost of something is equal to, let's say, for example, if it was, we're looking at the sides, for example, it would be $2 per square meter, $2 per square meter, multiplied by the actual area of those sides. Meaning that to find cost, what you do is you multiply the unit price, or you could call it the unit cost, times, and this is the unit cost per area, times the actual area. And if you multiply those two things together, you get the total cost of that piece. So that's what we're going to do here. For the top and base, we're going to have the unit cost, which is $8, times the area of the top and base. Now, what is the area of the top and base? Well, for example, the top. We have side length x and side length x. That means the area is x squared. Similarly, the base is also x times x. So in other words, the total area of the top and base is going to be 2x squared. For the sides, for example, let's say this side, it would be x times h. And similarly, all the other four would be x times h. X times h and x times h. So we have xh, oh yeah, the cost per unit is 2, and then there's 4 of them. So our total area is going to be 4xh. Okay, that means that our cost, if I multiply this together, I'm going to get 16x squared plus 8xh. Okay. Here you can see the cost is in terms of two variables, x and h, but we wanted to, when we're doing optimization, we want to write this in terms of just one variable. So we want to eliminate one of the variables, and that inevitably means having a relationship between x and h. And this is where the part where the volume is going to come to play. We know that for a box, volume is length times width times height. Okay, so let me just write this over here. On the one hand, volume is 32 meters cubed. On the other hand, it's also length times width times height. In this case, that's x times h, or x squared h equals 32. And you can see this is an equation between x and h, which we can now solve for h. So to solve for h, I'm going to divide both sides by x squared and get h is 32 divided by x squared. Now I'm going to substitute this expression for h into here. So I'm going to have this 8x multiplied by 32 over x squared. Okay. If we simplify this, we're going to get 8 times 32. Turns out it's going to be 256. And then we have x divided by x squared, which is going to leave us 1x in the denominator. Okay, so now we have c, or cost, as a function of only x. And that's the key. Now we can optimize. What we're going to do is we're going to take the derivative of c with respect to x. We could call that dc dx. And when we take the derivative, we use the power rule here. So we're going to get 32x. And then this is x to the negative 1. So that's going to become negative 256 x to the negative 2. And x to the negative 2 is the same as x squared in the denominator. Now, again, we're trying to find the minimum cost. So we're going to try to find critical points for c. And that involves finding when is the derivative equal to 0. Okay. So then we have to solve this equation. One way to do it is to clear our denominators. We have an x squared in the denominator. So what I can do is multiply both sides of the equation by x squared. The right side will just be the same as 0. The left side, I will get this second term will cancel out. So I'll get just negative 256. That's the point of multiplying by x squared. For this term, we get 32. We already have an x here, so it's going to become x cubed. Okay. Now we have this equation. And the simplest way to solve it is just to isolate x cubed and then just take the cube root. So I'm going to move this over 256. Then divide by the number in front, x, 32, I mean, divide by 32. You get 256 divided by 32. Turns out that's going to be 8. And then we take the cube root of both sides. The cube root of 8 is 2. Okay, so this is our only critical point. And intuitively, it makes sense this would be, we could expect this to be the final answer. This is going to be the optimal x for the minimum cost. But to really ensure it's a minimum, we want to do a little bit of extra checking. Now, so let's look back at this question. First off, for x, you want to consider what is its domain. Well, this length, the only really restriction is that it has to be positive. So that means x just has to be positive. So our domain is kind of x greater than 0, or you could call this 0 to infinity. So to verify this as a minimum, what we can do is write to a sign chart for the first derivative, dc dx. And we can start at 0, because again, that's our domain, and then increasing values. Here's 0. Let's say here's 2, our critical point. And we want to test to make sure that it's a minimum. And if it's a minimum, we would expect it to be decreasing here and then increasing here. Indeed, if you plug in a value, a test point that's over here, and you plug that into the derivative, so this expression, 32x minus 256 over x squared. For example, you could plug in x equals 1. You will see you'll get a negative number. And if you plug in a value that's bigger than 2, you can choose any big number, so 10 or 100, and then just try to think about plugging that in. It turns out you're going to get a positive number. And so indeed, the derivative is negative and then positive, which means that it's 0 here. Or it means that this x equals 2 point is indeed a minimum for c. Okay. So now we know the optimal x value, but we actually want to figure out the dimensions. So that includes the height as well. To figure out the height, what we're going to do is we're going to substitute it back into this relationship. We have the height in terms of x. So I'm going to write here, height, 32 over 2 squared. And so that's 8 meters. Okay. So the optimal dimensions are x being 2 meters, or the base length and height width being 2 meters, and h being 8 meters. Okay. And that's your final answer. Okay, so let's just recap a little bit. What we did is we tried to find the function that we actually want to minimize, the cost function. And we wrote it in terms of some variables that we find in the problem. Then, because there's 2 variables, we have to eliminate one of them. And we eliminated h, because it was a bit easier. Only appears once. Then we take the derivative. The reason we do that is to find the critical points. And then once we found our critical point, that's probably our minimum. To verify it, we can use a sign chart. This is called the first derivative test. And then we get our optimal measurements. Okay. That's all for this question. If you found this helpful and you're interested in a full solution guide with step-by-step explanations for every problem for this past exam and other past exams, check out the solution guide in the link below this video. Thanks for watching, and I wish you the best of luck with your studies.